All right, so what we're going to now look at is second order differential equations. So second order differential equations have this form, right? Obviously, second order, second derivative, all right? And then a function in front of, all right, with respect to t or x or whatever, all right, next to each derivative. Now, the good news is that we are going to look at it, but usually we rarely look at non-constant coefficients. So actually that reduces our case down to just constant coefficients. And this is going to break into two particular cases. Homogeneous, when g of t equals 0, and non-homogeneous, when it is not equal to 0. So we're going to start with, of course, the simplest case, and then we're going to get slightly more complicated. The best part of all this is it breaks down to what's known as the principle of superposition. If we have a function, all right, that is the solution, all right, two solutions to the linear homogeneous differential equation, you can actually write this as, all right, a single solution, all right, with two constants associated to each of the individual solutions. And this tends to be the common form, all right, to the general solution to our second order differential equations. All of it boils down to this. Now, there's more complicated individual proofs that we're going to at least gloss over, but because, all right, the initial proof is pretty important, and with this one we're going to use a ton, we're going to run through that. So, for my differential equation, all right, constant coefficient, linear, all right, second order, homogeneous, because it's equal to 0 differential equation. I want to let one of the solutions be e to the RT. Now, I'm picking this because, right, if this is second order, that means I take two derivatives. Why do we love e?
Itself.
Because the derivative, it is the easiest one to derivate. Now, here's the best part. If r is a root to the characteristic equation, now characteristic equation is just a fancy way of saying a quadratic. Notice, right, if I replace my y's with powers of r, I actually get a quadratic. And this is what we refer to as the characteristic equation. This is why differential equations is the best, because solving higher and higher order differential equations really just means boiling down to the algebra. All right, back to our equation. I need to take a couple derivatives. With my given y of t, when I go and I plug that in, to my homogeneous second order differential equation, and when I plug that in, I can immediately factor out e to the RT. And this is the point. This is the characteristic equation, the quadratic that we just talked about above. So then I have two equations to solve in order to find the actual solutions, right? E to the RT equals 0, and this is then a quadratic. And we'll identify, it can yield various solutions. We're going to start with, right, this yields solutions. R1 and R2. Over here, right, e to the RT, what's the graph of E look like? So where does it cross zero? It never does, right? So can never be zero. Which means the only solutions, all right, are the two solutions to the quadratic. You solve a quadratic down, all right? I plug in what those R's were. We're just calling them R1 and R2, all right? And I actually have my two solutions to a second order differential equation. All those first orders that we did, right? Were any of them super short? No. Actually, second orders are easier to solve than first orders, right? We did simple linear first order, right? Integrating factor. We had exact differential equations, Bernoulli, and separable. Separable is the easiest level, and we still had to integrate. What did we have to do here?
Couple derivatives.
Yeah, that was actually just the proof. Oh. The actual solution is solving the quadratic, right? Which actually boils down to every time we solve this, you solve the characteristic equation, all right, in order to get the solutions. And it is always a combination of those two solutions, all right, with E. So we're going to talk about this is nice enough, and we're going to prove why that is next week, okay? But we picked E mostly because it's like, oh, it's easy to derivate. But there is actually a reason that we're picking E, all right? And we're going to talk about that next week. So to go and solve this, so I want to solve the IVP, all right? And now notice that I have two initial conditions because whatever power you have, all right, you need that many, whatever order you have, you need that many initial conditions to solve it. So the whole point here, every time is to set up the characteristic equation. Y second derivative minus 9y equals 0. That means r squared minus 9 equals 0. Solve that down. R equals plus or minus 3. The general solution then, y of t, so using that principle of superposition, that becomes C1, all right? So now we do have multiple constants, right? So that's important to note. E negative 3t plus C2 e to the positive 3t. So our general solution, we can get to it that fast. Then, all right, the IVP is the only other part we need to do. So in order to do the IVP, I need to take a derivative. And then I can set up my two IVPs. Now, this is not difficult to solve, but I just want to refresh us on one little note here, right? Okay, so we get these down, right? Plugging in my zeros for t and the corresponding values. This then ends up being C1 plus C2 equals 2, negative 3 C1 plus 3 C2 equals negative 1. How do I go about solving that?
Solve one, plug it into the other.
Absolutely, substitution. Well, what's a way better method?
Combine them, combinations, so you can just add them top to bottom.
Elimination.
Elimination.
Okay. What wonderful piece of technology do we have that does elimination quick?
Calculators.
Calculator. What about if I write it in this form? What is this called?
Matrix.
A matrix. Okay. Get in the habit of just putting this in the calculator and solving it with the matrix. Mostly because this one you're absolutely correct. I do some by hand elimination or substitution, sure. Our number is always going to be this nice. Nope. Okay. So it's just get in the habit. And do we remember what the command is in the calculator? Let's just practice this one.
Barely know how to use these things.
Do you have one though? Oh, congratulations, Josh.
Right.
Okay, so second x to the negative 1 button is matrix. So it's left of the sign button. You see it? All right. Are we with me? Mm-hmm. Okay. Then scroll over to edit. And I'm going to create a 2 by 3. This is a 2 by 3 matrix. All right. There are 2 rows and 3 columns. 1, 1, 2, negative 3, 3, negative 1. So I plug those in and then hit second quit. Then I go back into matrix, over to math, and down to, for me, it's B. RREF command.
Reduce row echelon. Is that what that means?
Reduced row echelon form. All right. And then make sure you then put your matrix into that. Okay, and this is quotes because that's just what I selected. So it'll say RREF of my matrix. And then, as always, one last thing. Math bracket. Because that actually gives me
Perfect answer, or
exact answer, right?
sorry.
I was like, now, the best thing is you always do math bracket because if it still comes out as decimal, that means
It's not or
it's
repeating, or there you go.
yeah. So it means it's not worth a fraction, and I am going to write the decimal. But I was like, when you can, we write that out. So that actually gives me, and then remember what this becomes. So how I entered it, right? This was C1, C2, and then write the solution column. So make whatever it is, make sure you have that written out. That means C1 equals 7/6, C2 equals 5/6. And then I can put it back into my equation, my general solution. I now have my actual solution. YT equals 7/6 E. What was my first one? Negative. And again, of course, well, 3t, negative 3t, these will, right? If you did it the other way, these of course will solve the same, just an FYI. So I was like, are we okay? We're good with the calculator. Josh, we all good? Okay, good. I was like, that's so pretty to see that. And so the whole idea is that that's basically also because we are going to do higher order, so we're going to get more than just 2 by 3. Most of what we're going to do in chapter 3 is 2 by 3. Okay, but all right, as we proceed, we are going to do higher order. So it's just way get in the habit of doing that, and it just solves it. No muss, no fuss every time. All right, so I stated that when we solve a quadratic, we always get real distinct roots, right? 2 different roots. But we know, right, solving quadratics, there's actually 3 possibilities. You get 2 solutions, right? The parabola crosses the x-axis twice, all right? When do I get complex roots? What would the parabola do there?
Not exists.
Well, the parabola exists. Where is it crossing the x-axis? It's not. It's either completely above it or completely below it. Absolutely, right? And then the last one is a double root, all right? That is, both solutions are the same. How does that look on a graph?
Origin.
Yeah, it crosses at the minimum or maximum, right, of the parabola. So the blanking on the word. What do we call that?
The x right intercept, the x intercept.
No, at the bottom of the parabola. It's called the minimum maximum.
X.
Yeah, the apex. There's an
That's
official
not the word.
word.
That's not the right word though.
It's like I'm like feeling what it is. Yeah, it's the min or the max, but it's called vertex. Jeez, I have a complete brain fart. Did you already say it?
I didn't say very loud though.
Oh, the vertex. Okay. Okay, so real distinct. All right, this is the case we just looked at. We have 2 different R values, okay? And for now, just trust me that these are nice enough solutions. All right, it's called something important, but we're just going to call these nice solutions for now. We're going to prove that a little later. But all of this boils down to solving the characteristic. All right, we're going to be looking at linear homogeneous, all right, second order differential equations, all right, for basically the entirety of this chapter. So when we go to solve this, all of this is always going to boil down to the characteristic equation. And then we just have to solve that guy, which means we need to refresh just a little bit, okay, on...
Quadratic.
Yes, I could do quad form.
Complete the square.
I could do that one too, but there's a much cleaner, much more beautiful that all mathematicians love way of solving quadratics.
Factory.
Factoring, all right? So, all right, factoring. And I love the diamond method. Does this look familiar?
Yeah.
Okay, good. So you guys both know it?
8 and 3.
8 and 3. All right, but remember, if I have AC diamond, I have to go all out. Okay.
I haven't the diamond thing, man. That's you're blowing some cobwebs off. You know what I mean? Like
I was like, this one is super easy because when that term in front of that is just 1, we can solve that down very, very quickly. But yes, quad form always works as well. Factoring is just so beautiful. It's so elegant. And the really elegant thing about this is after solving a simple little algebraic formula, I have the general solution, 1 step. The only thing we need to do, take a derivative and solve for the IVP. But that is the general solution. And even getting the IVP is not very difficult either. Because we have ease, which really makes our solving pretty easy.
Why is that positive 8?
Because I lost my sign. And so again, it is solving a simple quadratic, and then again, just plugging it in a simple matrix every time, and we can identify, right, our solutions to the IVP. Now, we have nice solutions to our roots, all right, but that is not always the case. And this is definitely what I want to emphasize with why I use the matrix, because a lot of times our numbers just end up very, very ugly. So again, second order constant coefficients, characteristic equation becomes and again, this I can solve with some factoring. Now, this one also has another emphasis, 0, right? So if one of the solutions is 0, that's perfectly acceptable. Our differential equation, right? Still plug it into the principle of superposition, but notice what our differential equation actually becomes, right? E to the 0t, 1. So that actually just reduces down, but we still have another constant in there that we need to solve to find, all right, the actual solution. So then, all right, and usually notice already in the, I could tell from the beginning that this is going to be more annoying because in my initial conditions, I have -2 as the t, right? Which also means, oh, the numbers are not nearly as pretty. So need a derivative, but all the rest of this is just detail. I was like, we found the general solution, all right, which means then we just have a matter of doing a little bit of solving in order to actually find, all right, our solution. Okay, that goes away. 5 force CT. Right, and both of those ended up being rounded numbers because I got e to the negative exponents. One other thing, all right, notice this wording, all right, we've been doing this from the beginning. It's gonna become more important, especially when you're looking at the home fun and upcoming quizzes for this material. Actual solution, all right, and general solution. General solution, right, is when we have all the constants and we do, the hard work is done there. The rest of this is just details to get to the actual solution, which satisfies the initial conditions, okay? So going to be emphasizing that notation a little bit more as we go. We okay with the solving? Nothing too tough. All right, let's do it. Now notice, all right, what do we look for in this one?
The characteristic?
Well, yes, absolutely.
Oh, just the general solution.
Just the general, because it does not have
Any conditions.
conditions, right? This is not an IVP. So these actually are my favorite because you can do 100 of these, all right, really, really quickly because all I have to do is, yeah, characteristic equation and solve it down. This is the definition of plug form all the way though, because I can clearly see nothing with 6 multiplies, right, to -2. Let's see, 2√11. Just to be precise, again, be precise when you can. I was like, be aware, if this was an IVP, I would be doing the decimal all the way. Okay, but since I'm actually just going to the general solution, this one I can actually write out precisely. Because I can actually be precise with this. All right, so as always, it's kind of judgment call. Be precise when you can. As soon as then, when we go to IVPs way too often, I mean, I'm going to decimal like as fast as I can because it's just easier to handle. I was like, but I can actually be precise because this one just said general solution. All right, the other case. All right, the next case. So real distinct. Find the values, get them exactly, plug them in. All right. When you have complex roots, all right, it's because, all right, when you solve it down, we would get, right, complex A plus or minus BI, right? Complex form. When I solve the quadratic, I'm ending up with negatives under the square roots. Notice what that becomes. When I plug that in, I have A plus BI form in the exponent. This is the definition of whose formula?
Euler's formula.
Euler's formula. All right. This, all right, and this is what we talked about briefly, right? This is the actual generic equation, Euler's formula, which is a variation on de Moivre's. All right. So, and then just as a note, sidetracking. when theta equals pi, let's do this one just because it's so fun. E to the I pi equals cosine of pi plus I sine of pi. Okay, so that becomes e to the I pi equals, what's cosine of pi?
-1.
-1. What's sine of pi?
0.
0 times I is
0.
up. And then I move this over.
Voila.
And this is Euler's identity, the most beautiful formula identity in all of mathematics. So just as a fun note, tangent that we had talked about last time, just so now you know where it comes from. But here's the use, okay? So Euler's, okay? And I basically wrote the proof out for us so we could just discuss it, all right? Because what we're gonna do, I was like, there's a few things in math that I like to look at, proofs here and there, but since I'm an applied mathematician, I was like, I don't enjoy this as much as like David does. I was like, I'm about the usage of. So a couple of interesting notes, right? We break it up. We basically use Euler to convert it. And then through a lot of detail algebra, all right, and distributing and such, I can actually get my equation out and identify that, oh, with the sum of these, I have a bunch of constants and i's in there, and it all boils down to two equations, sine and cosine, because up there we use the sum difference product to convert sines to cosines, all right? And it boils down to our solution, all right? The same one that we had above, the principle of superposition, C1 e to
Lambda.
lambda. I was actually saying, notice what's not here anymore.
R.
Imaginaries, i's.
Oh.
I was like, well, we don't have anymore because we used Euler's to bring that imaginary out of the exponent. Because an I in the exponent, not helpful. I was like, so we brought it down, and with across, like messing around with the coefficients and the constants, we actually end up, all right, lambda and mu, all right, with our values that'll come out of the solution of the characteristic equation, all right, we convert imaginaries to something we can actually use. And so that principle is the one we're going to use. But basically, this all comes down to the characteristic. Like I said, there's going to be three possibilities, and there's going to be three different principles of superposition. But each of them, with practice, you're just like, oh, it always ends up being this one. All right, to that end, let's look at an example. Once again, quad form, and again, this is one where we could just plug in. So 2 plus or minus I root 5, right? And simplifying this one down. So, all right, we have e's and then the basically the exponents of the e's, which is always going to be the real piece. And then what is in the sine and the cosine, right? The theta will always be what's next to the angle. We identify it, and then we actually, once again, that's the general solution. Basically, the hard work is gone. Let's take a derivative and identify.
It's supposed to be 2C1.
C1. So this is first. C1 first. Derivative of the second. It's the second. I was like, you know. The annoying part about this, without a doubt, right, is that we have to, right, product rule this. Okay, but it was like, okay, I see anything that goes with that. That's C1,
Yeah.
that's C2, so
Nothing really goes away.
the details get a little. But luckily, I got y of 0 and y prime of 0, so a lot of stuff should be easy. A lot of that will go away. Okay, sine's a 0. Because actually C1 should say that's C1 equals 0. Alright, that's 0, that's 1, and 2 equals 0. And then with some solving, we could get C2 equals negative 8 √5. So with a lot of zeros, that all does go away. It actually becomes pretty nice. Again, back to my favorite. So the details in IVPs can be a little annoying here and there, but I was like, general solutions are always my favorite. And as we see, as our problems, we're gonna bounce back and forth between solving IVPs and solving general solutions. Because as the problems get way more complicated, we're gonna go more general solution than IVP. And again, be precise whenever we can. I could solve down, right, the characteristic equation and find the general solution just with some very, very simplistic, it was like algebra, quad form, factoring, leading square, whichever method you prefer. All right. All right. Last case. So end up with imaginaries, end up with reals, and then we can end up, right, with a double solution, right? Multiplicity, right? And you may recall. The big thing about this one is that if you have the solution where you have the multiplicity and, right, R1 equals R2, this is not a nice enough solution. The solutions have to be distinct, all right? We're going to get way into this in chapter 4. But even in the end of this chapter, we're going to show that you can't have two solutions representing the same value, right? And actually, maybe not. The idea is that, all right, with the solution, all right, in order to do it, we would have to do reduction of order, which we're going to talk about in a little bit as well. You do reduction of order because one solution is a multiplicity of the other solution to create distinct solutions, all right? When you plug this multiplicity in, right, because, oh, we're at the vertex, there's the vertex vertex solution, right? R equals negative b all over 2a. With some heavy algebra, plugging it in, taking two derivatives, we would get our double root solution. All right, integrate, and this also should look very similar, like Bernoulli's, by the way, but this is really reduction of order. And what we end up seeing is that we have our solution, and the other solution is a multiplicity of that first solution, which ends up being some constants, all right, and a multiplier of t. And that's the big part. When you have a double root, you can have that entire solution, since they both have whatever the vertex is, and they look very similar, but notice this one is a multiplicity of t. As we go higher order, that's going to be actually the thing. If I had a third order differential equation and a third solution, this one would be e, t times e, t squared times e, and we can go forever, right, to create distinct solutions, even though, right, the characteristic equation or whatever higher order polynomial we would have to factor, we keep whatever multiplicity that is, we just keep adding the variable and creating distinct solutions. And that's going to be a big thing we're going to look at later. So, but for our two-dimension case, all right, when you get a single solution, that's actually really good news for us because it just becomes e to the RT and t e to the RT. So let's look at an example of that. This is a good time. Actually, just looking at this is a good time to talk about two different things. One, I was like, you can recognize this and pull this apart. If you can't do that, this is where we can talk about the AC diamond method. Should we do that? How familiar are you guys with that? AC diamond? Okay. Let's do the AC diamond. I can actually look at this and identify exactly what this factors to, because I was like, just look at the first term. What times what makes 16r squared? What times what makes 5?
5 times.
25. I already gave it away. Yeah, fuck. What times what makes 25?
5.
Because I could just look. And then if the sign is negative, what are the signs here?
Both negative.
Both negative. That's exactly correct. And then, I mean, just looking at this, right, I can FOIL this out and it'll become this. While we're at it, though, let's take just a brief moment and talk about AC diamond. So, 16 times 25, this is how the AC diamond works. Take the first term and the last term, and that goes right here, 400. The B term goes down here. This is the multiplied term up top. Then I basically identify over here on the edges, what I want to figure out are the factors. What multiplies to 400 and sums to negative 40? All right. And now be aware, the signs are going to matter. So if that's a positive and that's a negative, what are both numbers? Are they positives or negatives?
Negative.
They're both going to be negative.
I'd say they both be negative 20.
Yeah. And so it's literally just identifying the factors. Negative 20 times negative 20 makes 400. Negative 20 plus negative 20 makes negative 40. And that's how the AC diamond works. Identifying the values. What you do then is rewrite the B term using the factors. So I have 16r squared and I still have 25. Now I rewrite the B term with my two factors. So, all right, it was negative 40 And basically, we're just breaking it up. Negative 40R becomes negative 20R minus negative 20R. Are these still equivalent? Yeah. Okay. Then, how do you factor 4 terms?
Like pairing or grouping?
Grouping. That's exactly correct. Then you just perform factor by grouping. So, what can I pull out of the first 2 terms?
R and 4.
4R. You're exactly correct. What can I pull out of the second 2 terms?
5.
Almost.
-5.
Negative 5. Super important because we need the signs to match. When I pull negative 5 out, that leaves 4R minus 5. How do you know grouping worked?
You got the answer we started with, or those are the factors?
These match.
Oh, okay.
Those, what is inside, and that's why if you only pulled out 5, this technically would have said negative 4R plus 5. So you pull it out, and the 2 insides match, and then you factored 4R minus 5 all the way out. When I factor 4R minus 5 all the way out, what's left?
4R minus 5.
4R minus 5. And now, this one is a perfect square trinomial, so it's not always exactly the same, right? I just want to refresh us on factor by grouping, which I could also then write as 4R minus 5 squared, right? Just since by definition we're in the double root case, this is a double root. But I just wanted to refresh you guys on the AC diamond method, all right? And you can always factor with this as well. So once I have that, back to where we were, 4R minus 5 squared equals 0, which of course gives us R equals 5/4, which means we can identify our general solution. Y of t equals C1 e to the 5/4 t plus C2 t e to the 5/4 t. And then from there, we can identify, take derivative, and solve the IVP. And then I was like, we're able to solve that down to get the actual solution for the IPV. Again, biggest thing is just doing that initial factoring. Once you have the quadratic solved, all right, there are 3 cases, all right? We looked at all 3, so it's important to understand if you have double root, 2 distinct roots, complex root. The general solutions look different. All right, one last one. General solution, all right, of y second derivative plus 14y prime plus 49y. This one we should be able, you can see this one though, right?
Mm-hmm.
R plus and it's always just, I was like, and because this concept we're going to do a lot, going to extend these out. So super important when we, because technically, that's not our -7 is not the actual answer. It's r equals -7 multiplicity of 2, right? Is that word sound familiar? Multiplicities, sort of algebra term. Again, this is why I love DPQ. It's all that algebra. That 10 years of algebra you had, I know everyone had 10 years, okay? I was like, it's just how rusty is it? So we're gonna keep refreshing on all this, all right? Okay, I have a little bit of time. I wanna look at reduction of order just because there's a couple of important principles. So, reduction of order. Everything we just looked at was constant coefficient. Reduction of order has non-constant coefficient. So I said we're going to look at a couple of these. Good news for us, we are only going to look at reduction of order examples of this one type. All right, this is in the home fund, all right, and on the upcoming quiz. This also, I have to talk about this one because these are Cauchy-Euler equations. And since Euler is my favorite, all right, these are a very particular type of equation. Notice the form, okay? T squared, T, no T in there, of course, homogeneous. So we have our functions of T, all right, are simply just T squared, T the first, right? So they're also quadratics, matching the quadratic of the order, right, of the derivatives. Reduction of order is actually really, really interesting. So it was in both of those proofs we just looked at, the double root proof and the imaginary solution proof, because basically is what it does is it takes a solution you have, then you identify a multiple of that solution to find the other one. Let's look at an example to actually get through the details. So important part, and I think maybe there's one in the home fund that doesn't start with the solution. But in all these cases, we start with the solution, okay? You basically have to start with the solution of the equation in order to find the second solution. So basically, just like we did in those 2 proofs, we started with, oh, well, it's got to be e to the RT, and then a multiple of that will find the second solution. Because basically what we do is we say let, all right, y2, because that's what we need, right? We need y2 be some multiple of y1. Some function that we don't know, and since y1 is t to the -1, I could plug that in. Now, in order to do this, I'm gonna drop the v of t and just write it as v times t to the negative one. I'm gonna take this guy. All right, but again, remember this is v of t, all right, which is why I wanted to write it explicitly up here. Because I need to plug this thing, in order to find the second solution, I need to plug it into my equation. So guess what I need to do with this?
Solve in terms of t.
No, this is y and y. But I have y,
Take derivatives of that.
I need to take some derivatives. This is where the real work of this problem comes, right? Because I have to take two derivatives, and when we start getting higher order, 3, 4, and 5 derivatives, and already, right, this is product rule, and each time you have product rule. So we have our equation, then we have to plug all these derivatives into it. And then the real work here comes in just rainbowing, distributing, and simplifying this down. The other important thing, remember when you're doing these derivatives, right, that it's super important. We're just doing product rule, but remember this is v of t, so we have our v primes in here. Once I have it all plugged in, then we can simplify this guy down. Okay, here's where the actual reduction of order is. So this method is called reduction of order. When we're saying order, what is basically order representing in our differential equation?
Power.
The power of what?
Derivative.
The derivative, right? Order is the, like, what number derivative we're on, right? Okay, so reduction of order. So if this is currently a second order derivative, by definition, reduction of order means I want to turn this into a first order, right? I'm reducing it from a second order to a first order. And that's basically what this method is. So in that case, I'm going to let W equal V prime. And hence, W prime equals
Or
V double prime, you're absolutely, that's exactly correct. So now notice what our equation is going to become.
we can integrate factor this. Wow.
Go ahead. What?
We do the integration factor, right? And do the
Integrating factor, because Josh, what kind of differential equation is this?
linear first order.
Simple.
Differential equation.
Yep. Linear, first order, simple differential. It's fun stuff. I was like, you have to appreciate the details. All right. I mean, I guess you don't have to, but you should. I was like, yes. And then remember, most important part of that is actually form. So W prime minus, this will be 3 divided by 2t W equals 0. And this would boil down to WT equals C, all right, since that is a first order linear simple differential equation. And then now we've gone way down the rabbit hole. What were we looking for?
The second solution.
Let me rephrase. What variable do we want?
B 1/t.
I want T's, all right, but I need to get all the way back to
Y.
Y. I need Y. Okay, so reduction of order, we're all the way into W. Okay, so let's start going back now. So we went all the way to W, all right, we found something with T, okay, now we need to start going the other way. So V prime equals W, right? That was our substitution. That means V of T will be the integral of W dt, which we have here. Now, here's the other big thing. Okay, so we have that CT to the 3 halves. I'm integrating, right? Now I have C and K. Remember the principle of superposition, okay? It has the form, right? This is just one of them. But what is in the equation already?
C1 and C2.
Constants. So we already have our constants really taken care of, which means that in this guy, I can dump these constants away. Okay, it's irrelevant. This 2/5 C, well, 2/5 times C becomes
Just another constant.
another constant. All right, add a K. Oh, I just have another constant. So our constants are actually taken care of, which means the only thing we care about is T to the 5 halves, because that's what we're actually trying to identify. We're trying to identify Y2. One last piece. So I got my V of T. And then lastly, Y2 of T, we defined it from the beginning, was V of T times Y1 of T, because, all right, one solution is a multiple of another solution, all right? Just have to figure out what that is. V of T is now 5 halves, and Y1 was T to the -1, which means Y2 is T to the 3 halves. Finally, Y of T equals C1 T to the -1, that was literally given to us from the beginning, plus C2 T to the 3 halves. And that's what reduction of order is. Taking one solution, finding the second solution. And basically that process were those two proofs that I skimmed over. They were basically doing this. Because I have one solution, I need to find the others. All right. And so notice, right, just to make sure, somehow this was given. All right, this is always given to us. Like I said, I think there's one problem in the home fund that like, I'm like, oh, find it, but really it's not even find, you basically have it. Okay. All right. I think we will call it there for the day and the week.
Thanks for this class.